short wavelength infrared to visible, from 1.5 micron to visible on time, or also from 980 to all types of visible and infrared photoluminescence bands. And in particular, this paper in 2011 it shows that really is excitation at 1.5 in these nanocrystals, and these nanocrystals are fluoride nanocrystals. And the under excitation crystallinity. This kind of all spectrum with a down conversion and up conversion wavelengths.
Probes is optical coherence tomography imaging for dental materials into tools. This was done in cooperation with our colleagues in Brazil. And actually, this is also tools. This is photoluminescence, part of dispersion of nanoparticles covered with tools. And then we made some about difference in scattering of this photoluminescence. That this dark places part of this arrow show the case area of tools. So this can be kind of prospective direction. And this is also not published, just demo how this light infrared can come through human skull can be imaged. This is just paper soaked with nanoparticles, and you can see it through this. This is recently accepted in Journal of Biophotonics. We did measurements just because we want to explore properties of tissues, biological tissues, with further infrared and short wavelength infrared, and we can clearly see different optical, in addition to traditional NIR1, there are other windows of optical transparency, and all of them can be used for photoluminescence imaging. And this is also, we did with nanoparticles, this is cellular staining and in vivo staining, with neodymium top nanoparticles, which, and actually this is ionic neodymium directly excited at around, in this case, 750, and it has all spectra. This quantum yield of photoluminescence of this nanoparticles is quite high. It's around 40% in organic solvent, 22 or something in water, and can be used as beautiful imaging probes. And this is quite recently, it's just published 1 month ago in the Glass Optical Materials about another particles which is produce that emission, photoluminescence emission in short wavelength infrared range. We get 1.5, around 1.5 microns, and the excitation at around 800. So this is actually excitation in the first infrared window of optical transparency, and emission is in second window. And actually this allows for images through tissue imaging. Is just mice injected with sub-Q injected with this nanoparticles injection with suspension, and you can see the photoluminescence coming through hair, for example. And this is the same nanoparticle, same paper that we demonstrate through skull imaging. Also excitation is this window, and emission is here in this window. And actually, this is in vivo imaging through skull blood vessels in the brain vasculature at 1.45 microns. This is just that also down conversion quantum yield of this core short nanoparticles around 11%, which is quite high for this spectral range. And this is actually one more example of convenience of this type of nanoparticles. This is poster which is presented at this conference, and member of our group, Artem Yakov, this is his work, and he will be presented this, how because of very nice and spectrally distinguished photoluminescence, you can unmix different, even this near-infrared dye. And then, this is in vivo, different imaging. After application and mixing, you can distinguish where is dye, where is nanoparticles. So, possibility for multiplexing is all multiplexed. So, what is wrong with these nanoparticles? Why we need dyes? So, despite of recently achieved promising results on composition and advancing this rare isotope nanoparticles, actually there is a problem, inherent problem, that limit is associated with nature of that FF electronic transition in ions, in rare earth ions, and that means that very oscillator strength and transition is very probability of absorption cross-section is very low. So if you can see critically small absorption cross-section, so this is where it's actually 10 power 3, 10 power 4 times less than organic model. So even if quantum yield is high, brightness of this probe is not very high, because brightness that involves absorption too. So, and actually, really, that's a big problem. And to solve this problem, that was proposed in 2012, this paper by Zhu and all about sensitization of convention with dye touched. They attached to the nanoparticles dye. This is for first. This is emission of dye and absorption of nanoparticles. In this case, this is a technical absorption. And you can see how efficiently changed photoluminescence intensity without dye and with dye. So, and this is actually increasing additional excitation of rare earth ions through harvesting infrared light by this antenna near infrared organic dye. And this is really this particles, this tutoring article published last year Chemical Society review, this explains what is possible with the first particle and texture energy transfer from dye to rare earth ions. And this is in this case like from the surface, if you apply some dye and to adjust the core, and this sensitizer, we can call it donor or activator, and we can call it acceptor. So this is actually, so this is like stepwise energy transfer. In this case, it's mostly first energy, first mechanism is involved. In this case, partial. And then we decided we went deeper into that and developed so-called energy cascade conversion. This means that we introduced intermediate step from dye energy transfer to neodymium and then neodymium to detective and then up conversion. And it works more efficiently. And what is important is the speed of this system. And really, you can see that under 800 nanometers around excitation, that emits in blue. This is this emission. And if you can see by eye, this is 3-photon emission. And 3-photon emission, to get it in this usual nonlinear excitation, is very tough. It requires ultra-short pulse laser. Here it is actually achieved with just non-coherent length. So efficiency of this process is very high. This is next paper published moving into that direction, as to introduce a multi-dimensional energy transfer. Here, different pathways are involved in transfer of energy from dye to activator, and then followed by convection emission. This is different. You see the lifetime of donor dye is shortened by energy transfer. And then also the same application, just showing the different activator ions can be here as erbium, thulium, polonium used, and also this is through terbium and dye. And also this is not directly with the same nanoparticles in the same paper showing that they can be docked into some transparent matrix. In this case, it's PDMS siloxane-based matrix, and some pattern can be created. Even if this is not directly related to bioapplication, but still I would like to show this image. Okay, so that next I was talking about up conversion, but similarly, that down conversion process also can be synthesized by energy transfer from dye, which acts as an antenna and then transfer energy to emitting ions. And it was published in this also in 2016. The different ions can produce under being excited through excited dye and energy transfer, in this case from neodymium, and then terbium, and then neodymium itself, polonium, rhodium, thulium, erbium, and then some kind of example of biological imaging was presented. How much more time? Okay, so then last example what I want to show, this is not one more. Yeah, just last example. Many people probably are familiar with photodynamic therapy. That when so-called photosensitizer or drug, this is therapy of cancer and other diseases. When this is Jablonski diagram illustrating processes, so this excitation of this organic molecule, mostly organic molecule, mostly porphyrin-based stuff, and then internal intersystem crossing to triplet state, and then from triplet state it interacts with molecular oxygen in the surroundings, and that excited single oxygen, reactive oxygen species, destroy, oxidize biomolecule and destroy malignant tissue and cells. So, and in this actually also quite a long time ago, multi-photon, two-photon PDT was proposed and demonstrated, and it also worked. But of course it has limited applicability because you need to focus ultra-short pulse laser to get to photon source. And actually, additionally, that photosensitizers, they are not mostly majority of that photosynthesizers, they don't have high photon cross-section. So for this different conjugation, people develop, I'm not involved here, not presenting here examples, but this is typical that some chromophore is high to photon cross-section combined with photosynthesizer, and then energy transfer is involved. And here also nanoparticles platform for two-photon PDT also being proposed, and we actually also proposed this 11 years ago when in silica-based nanoparticles combined two-photon absorber dye donor, which absorbs efficiently the multi-photon and then transfer energy through forceless resonance energy transfer to this photosynthesizer, which being excited generates input. And actually, based on this same approach, people developed, we were working, but we were not fast in this area, and actually these people from Singapore Technical University of Singapore, they did a lot, this Professor John, his group, which is his name, as well. They used upconvection nanoparticles to excite and to transfer energy to photosynthesizer and produce demonstrated quite efficient photodynamic therapy. And recently, this approach of dye sensitized nanoparticles and conversion PDT, these two approaches were combined, and this guy is also from China that develops this architecture nanosystem, which being excited through dye, and then also to ions in the shell and to core, and that light is used to excite that energy of converted energy excites photosynthesis. So here is conclusions of my talk. So by combining the advantages of organic dyes in inorganic nanoparticles, superb next generation of organic and inorganic hybrid nanomaterials with thousands of times enhanced better brightness can be achieved along with embodied curable and diversified excitation layers. And then aqueous dyes sensitized up-down conversion nanoparticles provide game-changing possibilities towards bioapplication, especially when considering the ability to be excited by incoherent, low-power, light, non-expensive light sources, such as even LEDs. And multidisciplinary efforts across chemistry, physics, material engineering, and biology, breakthrough in the development of the dye-sensitized LNG-doped rare earth-doped nanoparticles will boom, and new applications will emerge in the near future. And this is acknowledgement. This is dean of our college and all big biophotonics group, and this is people from my group who were involved in these materials who are presenting. And actually, this is also my former boss in Buffalo, and my dear collaborators, collaborators, Professor Gordon Chen, who was in Buffalo a long time and now in Technology, and Dr. Watson Lee from Wrocław University of Science and Technology, and Dr. Wei Shao, and Professor Sigmund King. And this is funding, which currently I have to proceed with this work. And this is Shenzhen, which is before sunset and after sunset. And this is Shenzhen University, the college is over here. And thank you for your attention.
Thank you very much for very talk, for excellent work, experimental and very nice idea. So we have time for discussion, and paper is open for discussion. Who would like to ask?
I want to ask you
More.
what type of material do you use as nanoparticles, and how are they compatible with living organisms?
See, this is a good question, and actually, really, we started working at all for this using luminescence conversion from, I believe, from the beginning of 2000 in Portland. And all the time we were working with oxides, and it was very tough and not disturb person. But then people found that fluoride, sodium yttrium fluoride, is a basic material. Forms very nice, low phonon crystalline nanoparticles, which allows for high intensity. So this is most of these four particles, this is fluoride nanocrystals. So this is actually ceramic nanocrystal. So they are actually not biodegradable, but they are considered as quite harmless and biocompatible. So they actually, in our experiments, we injected mice with and they for all life living imaging, and they disappear. So they slowly excreted, being excreted from the organism. But of course, for going into further, so for animal imaging, it's okay. Of course, if to come to application in humans, that's a different issue. That will require. So this they are inert, not toxic material, nothing. You know, this is, for example, sodium yttrium fluoride. You know, so, compared to quantum dots, for example, cadmium, which is something. Okay. Say it again. Yeah. Yeah.
And what about experimental improvement of efficiency?
2 photon? I used to know one person. He had a company, he patented, and he got big NIH grant. This is Professor Stanford from Montana University. He got some very preliminary promising results to 2 photon. But 2 photon has limitation in sense that you need a high power ultra short laser, femtosecond. And this is, first of all, it needs to be, this is very expensive. So compared to, you know, all ideas is to excite photosensitizers with near-infrared light. And actually, if you need to find focusing, you need to scan, for example. This is all complicated, expensive. Nobody wants to deal with this, especially people move towards photosensitizers, which itself absorb around 800 linear single photon absorption. So slowly that movement into that direction. The people still publishing papers, but it's very something special to go. For me, it's difficult to, because now, for example, I also have collaborating with people in the photodynamic center, photodynamic therapy center in also Parkinson Institute in Buffalo. They developing already
the last question, please. You can use this microphone.
Oh, my question touched also 2 photon absorption and the possibility to destroy the cancer molecules. So, of course, windows of transparency and so on, but 2 photons processes are non-linear, and so maybe to
Actually, it would be, like you say, if not ultra-short, but ultra-short pulsed laser is being used. And actually, people really already developed in vivo to photon microscopy, for example, very easily, because average power is quite low. You have high peak power with femtosecond pulse, but repetition in high repetition rate. So average power can be 50 milliwatt, for example, but peak power allows for a highly nonlinear phenomena to take place, so two-photon absorption. So that's you have, for example, you have, if this is 90 megahertz repetition rate of femtosecond laser, is around, for example, 12 nanoseconds between femtosecond pulses. You know, so this is, it is not heating.
So we have to finish our discussion. Thank you very much.
Thank you. Thank you.
Very interesting talk. And next talk, I would invite Professor Elmar Petrov from Bogolyubov Institute of Theoretical Physics, super exchange, non-resonance tunneling mediated by a molecular nanowire.
First of all, I would like to thank the organizing committee for possibility to present recent results that have been obtained in Institute for Theoretical Physics in Kiev. And the results concern molecular electronics. I would like to show some results which relate to super exchange tunneling, which is mediated by molecular wire. Molecular electronics start from the first paper of Averham and Ratner from about 40 years before. And the main purpose of this molecular electronics is to use separate molecules as the basic elements of electronics. At present, we have silicon electronics, and we reach the size. I'm sorry. Size. I do not read the rest of. Это вот этот самый, как его, указатель. Окей. Это указатель. А где указатель? Не вперед, не назад. I'm sorry, but it is not. Oh, okay. Molecular electronics suppose that after some experimental results, we can reach the size of transistor elements about 10 nanometers. At present, silicon electronics give about 20 nanometers. So, starting from the maybe 15 years before, experimental results begin to apply for investigation of conductivity of molecular systems and single molecules. Here, this scale shows that now silicon electronics is in this region, from this, and molecular electronics, maybe it will be possible to reach a size about 1 nanometer. Experimental results which can measure conductivity of molecules, signal molecules, very fine experiment. But now it's possible to measure the tunnel currents in this through separate molecules or molecular layers with use of scanning tunneling microscope. With use of this device, it is possible to not only to measure tunneling current, but to prepare the different certain architecture on the surface of monolayer. I want to discuss some results which refer to tunnel conductivity of molecular wires. Molecular wires are the system which contain from regular part of chain and terminal units which unhooked with tip or substrate. It is a very important system because monolayers is the fundamental plate for construction of different type of molecular devices. Experiments show that roughly the dependence of the current from the distance between the electrodes is shows the tunneling behavior, but it is not known is this law is held at different voltages. Maybe this dependence is more preferable. And now it's not clear. This question is this problem is not clear. The results of theoretical results show that approximately this law is supported, but it's not any molecular system and in any single molecule in molecular wires. So it is necessary to consider this problem is more from more fundamental positions. And I want to show some results related to physics of this tunneling process. First of all, non-resonance tunneling supposes that electron does not occupy the molecular wire and is transferred from one electrode to another electrode without any dissipation. Just this process shows exponential behavior or near exponential behavior. I show shortly or briefly several expressions, but I do not explain this expression because this is pure theoretical solicitation. The main problem is to obtain this value which determine probability of electron tunneling jump from one electrode to another electrode. The model which is supposed to explain the results is the following. We have two electrodes, contact units or terminal units, and chain. This is molecular wire. The chain is regular, and if we find probability to quantum electron jump from one electrode to another electrode, we derive this value which define this probability. So idea is super exchange is the following. Electron on this electrode has wave function which overlap with wave function of the first unit, the first unit with two second units and so on. So in the results we have effective, small but effective overlapping between electron wave function of conducting band in this electrode to another electrodes. It solves the problem. We, in the simple model, one level per one unit, we obtain some results. Only a couple words. The current has a rather complicated expression. Here is a transmission function which determine all physical process. If molecular wire contain terminal units, then this function can be divided as can be represented as the product of stress function. And the main information about the wire is concluded in this this function of a regular chain. In the model I noted, this function has such a structure. With attenuation factor, which has some parameter, which this physical parameter can be controlled by the structure of molecules and the structure of contacts. As a result, we can reduce complicated expression to the expression more simple, and in limiting cases, we can obtain standard form for tunneling through barrier, and another limiting case is deep tunneling. So the theory gives possibility to manipulate by the parameter and explain different regime of tunneling process. Integral form is very complicated, but there is some possibility which depend on the relation between the parameters when this complicated function can be represented in much more simple analytic forms. And these analytic forms can be analyzed experimentally. I give some results. The main physical parameters is the following. E is the tunneling energy. It's the energy of electrons which withdraw left electrode and come to the right electrode. This is tunneling barrier, not barrier, tunneling gap for and the gaps between terminal units and Fermi levels. Okay, as an example, I show the example on simple molecular wires. Is alkene chain is adhered by the sulfur atoms to the electrodes. It's possible to show that the simplest form for experimental analysis is this Gauss form. It's rather simple analytic expressions, and we can specify all parameters of the system. It's more complicated expression, but it's more exact, but they can be applied on at more high voltages. Now the results. At small voltages, we have ohmic law, and in ohmic law, we see exponential decrease of the current with increase of the number of chain units. We see that our approximated analytic expression very good coincide with experimental results. When voltage is higher, is a moderate voltage, we can see that simple Gauss law, which work very good at low voltages, does not work, but mean value approximation good follow to experimental results. At high voltages, we can see that Gauss it's not good, but good position is good results give mean-value approximation. Such situation is supported when terminal units are non-active and transmission functions change smoothly in the windows, in the voltage windows. Another situation is happening, it's results which show coincidence of experimental results to theoretical ones. The point are the experimental and the curves is the theory. Another situation is when molecular wire is attached to the electrodes via active terminal units. At small voltages, we have this same situation. Gauss and mean-value approximation follow good to experimental results, but another approximation, which corresponds to the resonance with terminal units, better. If at moderate bias voltage, we can see that terminal transmission functions have special peaks in within the voltage region. It is reflected in the dependence of the voltage dependence and length dependence. And at last, we can see that only terminal unit approximation, which take into account resonance within the terminal units, reflects good experiment results. So, the summary. Now we have in hand a rather good theoretical possibility to analyze experimental results in different voltage regions. Following this theoretical expression, we can compare the different mechanism of electron transfer, of tunneling electron transfers through molecular wire. Since molecular wires are very important elements in molecular electronics, we can conclude that our theoretical results may be useful for analysis of experimental results, not only on concerning the currents, but the conductance and resistance of single molecules and molecular wires. I would like to express the thanks my colleagues, including colleagues from our institute and colleagues which I have contacts with German physicists. Thank you very much for your attention.
Thank you, Professor Petrov, for interesting talk. The paper is open for discussion. Who would like to ask? Please, you can use this microphone. Maybe it would be for all people. Would be.
I'd like to clarify. Did you consider subsequent tunneling from unit to unit, or tunneling through all molecules?
You mean the scheme of creation of superexchange, yes?
Yes, I mean some part of molecules as separate unit, a tunneling subsequent from one to one, and through all molecules.
Yes,
what is the barrier?
Yes, it is the basics for mechanism of tunneling, superaction tunneling. Now I come back to the scheme. This one. You mean this scheme, yes? The overlapping between overlapping of wave function of neighboring sites, overlapping of end sites with terminal sites and terminal sites with electrodes. This overlapping also local tunneling, but generally we obtain long-range tunneling from one electrode to another.
Thank you.
Other question, please. Yeah.
Have you taken into account in your model so-called affinity electrons? So when a molecule has a contact with the surface, left, right electrode, the first act is that the affinity electrons go in or go out the molecule. Thank you.
Your scheme suppose real electron hopping from electrode to terminal units and along the chain. But superexchange tunneling does not support real occupation of these sites by electrons, only virtual population of all these levels. It's pure quantum effect. So in the non-resonance tunneling, we have no population of these units by the electrons. Electrons in virtual transfer across this chain is specific of quantum mechanics. If we have low energy of this chain, of course, in this case, the population of chain or wire units by transferred electrons is happening, of course, but it's another, completely another mechanism. In tunneling process, is not, really electron is not populate the chain.
Okay, other question.
I see you have the linear molecule, this is your model, linear molecule, in which maybe aromatic p-electron containing groups, yeah? Here, what was the model? What was the model? Maybe, and this is B, this is probability to jump of electron or no? And is the energy levels of these p-electron systems is equals or there is some distribution.
Energy of electrons is energy of tunneling. This energy coincides with one level here, left level, in conducting band of electron. But chain levels, it's transmissions from chain levels is delocalized, common levels chain. This
so separate systems.
Yes.
Thank you very much.
Okay. So
I will talk a little bit about our samples, and then I will talk about photoconductivity of carbon nanotubes and PCBM films. It's PCBM, it's a kind of Fullerian derivative. It's a soluble Fullerian derivative. Then about transient photocurrent dynamics, ultra-fast time resolve, charge transfer, and some memory effects. So carbon nanotubes, probably all of you know about carbon nanotubes, and these materials, structures were discovered more than 30 years ago, and of course then during this time they were very heavily researched, and interest always was very huge. Not only, last recent years probably the interest slightly reduced after discovery of graphene. It took some attention, but nevertheless these are very interesting materials because these are long one-dimensional, quasi-one-dimensional materials like spaghetti. Depending on the structure, they may be conductive, maybe like metals, they may be photoconductive. And there were many attempts to use this material in different kinds of, in different applications, and including electronics. So I just will mention several examples about how they are used in electronics. Just one of applications is narrow channel and thin film effect transistors, and based on these transistors, even carbon nanotube computer was developed. So it could be a kind of future electronics, because in fact it could be like nano devices, nano electronics could be made on the base of these materials. Another kind of applications they use in optoelectronics, for example, carbon nanotube and organic semiconductor, some kind of devices, including C60, were used in near-infrared photodetectors, because carbon nanotubes have absorption bands in near-infrared. Also, these devices were attempted to use as electron acceptors in blends with conjugated polymers for organic solar cells. So it's organic solar cells. These materials were used as acceptors and as charge carrier transporters, electron transporters, because carbon nanotubes have very, very high mobility of charge carriers. They were used also as electron donors with PCBM blends in all carbon solar cells, and quite substantial efficiency, 3.1% efficiency of solar energy conversion was achieved in these materials. Okay, so in order for further applications, we of course should understand very well what's going on under excitation of such materials, of such composite materials. And as I will show later, these processes are not simple, and quite many processes take place when we excite this kind of carbon nanotubes and PCBM blends. Okay, so in my investigations, in our investigations, we use just one type of carbon nanotubes. It's 6-5 single wall carbon nanotubes, so 6 spines defines symmetry of these carbon nanotubes. Usually after synthesis, mixture of different carbon nanotubes is obtained, and some particular species of carbon nanotubes, they could be separated by using conjugated polymers, and as it's shown here, these conjugated polymers wrap around some particular carbon nanotubes, and then these carbon nanotubes become soluble, and you can just separate from other carbon nanotubes which remain non-soluble. But of course, in these carbon nanotubes later on remain wrapped with this polymer. But this polymer does not make very big influence on electronic properties, because this polymer has wide energy gap, much wider than carbon nanotubes or, okay, so PCBM used here. Therefore, it does not influence strongly electronic properties. And as I told, we used also this Fullerene derivative, so it's soluble Fullerene derivative, and these Fullerene derivatives attached to these carbon nanotubes. So now we have such kind of electronic structure. As I told, here it's polymer energy gap, here is carbon nanotube energy gap, and here is PCBM energy levels. And in fact, according to this system, under excitation of carbon nanotubes should nothing happen, but still it happens. So I am not completely sure what's going on, or these energy levels are not very well defined, but nevertheless, as I will show later, under excitation of carbon nanotubes, efficient energy transfer to PCBM takes place. Of course, whole transfer here cannot take place because its energy gap very large, so it's only electron transfer. Probably this is related somehow with probability to find electron here and to find electron on this large nanotube, because here are much more size for electrons, so it's just probability maybe effects. Okay, so we used, in fact, carbon nanotubes are not very technological materials. It's relatively difficult to prepare samples. For example, usually these devices are based on thin film devices where our active material is placed between two plate electrodes, but in that case it's quite difficult to prepare samples because shortcuts take place and it's difficult to prevent this. Therefore, we used for our investigations a little bit different technique. We applied so-called interdigitated electrode comb. So here you see we have electrodes and we have spaces between electrodes, and we can apply voltage to these combs, and we have electric field here, and when we excite our samples, we have current going from one electrode to another electrode. So here distances are 4 micrometers one electrode and 4 micrometers another electrode. It's also like we have just gap between two electrodes, only this gap is becomes very long, and we have a possibility to excite all this area. We use samples, as I told, mixtures of carbon nanotubes and PCBM molecules. Here you see micrograms, images of these samples. So we used to prepare these samples from fresh solution and from aged solution, and these samples showed quite some different electronic properties. And this is, it's seen that, and when we have fresh solutions, we have long, like spaghetti type, these carbon nanotubes. But when solutions were aged for several months, they called some aggregates, and here these carbon nanotubes are just mixed between one another, and so just different morphology of our samples. Okay. Here is just the photoconductivity of CNT PCBM films. So, in fact, if we prepare just PCBM films, just carbon nanotubes films, they have very low photoconductivity. Here it's not zero, but it's almost zero. But adding of PCBM, conductivity increases. After reaching some PCBM ratio, conductivity starts to drop again, and this is because this PCBM is a non-conductive material, and when we have high concentration of PCBM, these carbon nanotubes become completely separated one from another, and current cannot pass through this through this carbon nanotube network. Okay. Right. Yes. Here you show, we investigated transient photocurrent investigations, and we excited this our sample and looked at photocurrent. Photocurrent by using 50 ohm load, photocurrent is relatively low, therefore we used integrating photocurrent measurement regime. So current passed like this, and it was integrated on this integrating capacitor. Therefore, our current is just a derivative of this curves, and later on is the charging of our capacitor. And as you see here already, we can see that samples which were prepared from fresh nanotubes, they have very fast just jump of voltage, show very fast jump of voltage, and later nothing happens, just little bit recharging at some longer times. And we interpret it like this, that when we create charge carriers, they move very, very rapidly through carbon nanotubes, and it happens faster than time resolution of these our measurements of several nanoseconds. But when we have all the samples prepared from H solutions, then in addition to this very fast photocurrent growth, we have also longer processes. And we interpret that this longer process, we have already electron transfer from one nanotube to another, which takes place on several microsecond time scale. At longer times, we also observe some current, so it's derivated, as I told, it's just a current, and this current is due to the electron transfer through PCBM system. So here we have separation between hole remains on our carbon nanotube, and electron goes to Fullerene derivative, and so electron can also pass through our sample, but only in case when we have high this Fullerene concentration. Okay, so here is transient photocurrent dynamics. When we increase excitation intensity, this slow part almost decreases, so remains only very fast photocurrent component, and this fast photocurrent component, this is understandable because in this case nonlinear effects takes place, like exciton annihilation and also fast charge carrier recombination. So in these measurements we cannot clearly separate two processes. One process is a lifetime of generated charge carriers. Another process is charge carrier mobility. So in these devices, mobility may be also very important because it may change with time. Why it may change with time? Because when we generate charge carrier, it moves through the carbon nanotubes, and for example, it reaches end of the carbon nanotube and cannot move further. Another process is, of course, electron-hole recombination. And we would like to separate between these two processes. How we can do it? There is such a kind of technique, time-delayed collection field technique, which allows such separation. In this technique, we use excitation when there is no electric field, and later we switch electric field later. So we generate charge carriers, and if these charge carriers survive during this collection delay time, then when we switch collection field, we can extract these charge carriers. Here we also can investigate dependence of carrier generation on the electric field strands, and also dependence of carrier extraction of the electric field strands. And so here we change generation voltage, so we use not 0 volts, but we use some generation voltage, and we look at the photocurrent when it's collected by collection field, and we see that nothing happens by changing this generation field, so it means that charge carriers are generated spontaneously. They do not need assistance of the electric field. But for extraction of charge carriers, we need, in fact, strong electric field. So here we change collection field, and dependence of the extraction voltage shows quite strong dependence. When we change the collection delay time, so here it's this photovoltage transients measured at a different delay time. So when delay time between excitation pulse and collection field switching is short, we have strong photocurrent. In fact, here is a collected charge. We have we collect quite sufficient charge, but when we increase the delay time, the charge collection drops down, and the transients slightly change their shape. And here you see so dependence of this extracted charge on the delay time, and as you can see, initially the extracted charge drops very rapidly during something like 20 microseconds, but it means that still charge carriers survive something like more than 20 microseconds, And later on, we have long tail lasting for more than 100 microseconds. So it means that some charge carriers may survive quite long. They do not recombine during this 100 microseconds. And we also see that there is difference between this rise time. So here is faster, here is slower. So when charge carriers, when we generate charge carriers, they apparently find some trap states, and then after application of the voltage, we should extract these charge carriers from the trap states. Okay. So here is a model of the transport of charge carriers through carbon nanotubes, and so under excitation of carbon nanotube, we excite carbon nanotube, excitons move. They found some contacts with PCBM, with large PCBM area, or with single PCBM molecules. Then charge carrier separation takes place very rapidly, and electron moves through PCBM, and hole moves through the carbon nanotube. If there is situation when electron is transferred to single PCBM molecule, then electron cannot move. We have photocurrent only because of hole transfer, and it's some kind of estimation that this hole transfer through single nanotube, it takes place faster than during 2 nanoseconds, but jumps to another carbon nanotubes are significantly slower. Now, what we can then, we decided to investigate this very fast initial photocurrent path, which we could not investigate by using our photocurrent investigation technique. So we used some more complicated technique. It's a little bit tricky. We investigated, in fact, electric field inside our material, just directly inside our material, by using femtosecond technique. This technique is based on so-called electric field induced second generation effect. So when we use ultra short laser pulses, we can generate second harmonic because of nonlinear processes, but this second harmonic cannot be generated in isotropic materials. So when we apply electric field, we break this isotropy, we make this material anisotropic, and then when this material becomes anisotropic, second harmonic may be generated. And so, in fact, here is dependence of the second harmonic generation efficiency on the applied electric field. So you can you see that at zero applied electric field, we have no second harmonic, but when we increase electric field, this second harmonic intensity increases parabolically, and in fact then, from the second harmonic intensity, we can determine what was voltage and in fact what was electric field inside our material. So in this, with this technique, we have ultra fast time resolution. This time resolution in fact is limited only by the duration of used optical pulses, and so using femtosecond laser we have femtosecond time resolution. So here we have also diffraction grating, and so when we apply electric field, our laser pulse diffracts into different directions, and so second harmonic diffracts to some particular direction, so it's here. Okay, so now if we apply another strong, so here is like a probe pulse which probes electric field, but if we apply strong excitation pulse, we generate charge carriers, and these charge carriers, by moving through our sample, they reduce electric field. And in this case, so we have this ultra-fast time resolution. Here is a setup. We have probe pulse, we have pump excitation pulse, we excite, and we look at the intensity of our diffracted beam. Here are some results obtained by using this technique. So the curves seems to be not very complicated, but in fact we can see several processes from this curve. So let's say just this is when we have only carbon nanotubes wrapped with this conjugated polymer. So in this case, charge carrier generation efficiency is low, but still when we excite with femtosecond pulse, we see drop of the electric field. So here is electric field. We see very fast drop of the electric field during just less than 1 picosecond, with limited by our time resolution, and this drop is caused by generated excitons. So when we generate exciton, we can say that we have electron and hole together. But when we apply electric field, this electric field separates electron and hole, and we have this separation increases the electric constant of the material, and when increases the electric constant, electric field drops down. So we have fast increase of oh, sorry, wow, I made something. Wow. We have fast decrease of the electric field, then exciton density decay, and here charge carriers are generated, and later on we observe charge carrier recombination. But when we have high PCBM concentration, we do not see this process. We see only charge carriers, and we do not see fast this exciton contribution, and therefore we come to, oh my God, again. We come to conclusion that we generate charge carriers during 1 picosecond, and then when we generate charge carriers, this electron localizes hole, and initially we do not have this separation between electron and hole clouds, and only with applied electric field we have separation of hole, and we see current on longer times. And so unfortunately I already don't have time to talk about longer times, but little bit. So there are also some memory effects. In fact, when we apply electric field, we can see photocurrent even after long time, even after 12 hours, for example. And this electric field initially is stronger, later on decays, and here we see decay of this electric field. So here is decay on 20 nanosecond time scale, which is very similar to the results obtained by time delayed collection field results. So here we observe very, very deeply trapped charge carriers, and so these charge carriers are trapped in so-called spatial traps. So we generate charge electron, and it goes to some place where when we reduce electric field, it cannot go back, and we have very, very long memory effect. Okay, and so my conclusion is rapid photogeneration and deep spatial trapping causes charge carrier dynamics lasting from femtosecond even to days. Thanks for your attention.
Okay, thank you very much for a very interesting talk. And we have time for one question. Please.
Very interesting talk. Can I ask a question? Did you try or ever try photoluminescence measurement, or in particular time result photoluminescence measurement? How is it correlates?
Okay, yes. In fact, we didn't try photoluminescence measurement of carbon nanotubes. I have some results here. We tried just photoluminescence when we excited polymer. So here, under excitation of polymer, we see energy transfer from polymer to carbon nanotubes, but unfortunately not carbon nanotubes. Not carbon nanotubes.
They may provide some information.
Yes, they may provide, but we also tried transient absorption measurements. Here are transient absorption measurements, which I couldn't, had no time to discuss, but here we observe also charge carrier separation. So here, without PCBM, we have just exciton decay, and with PCBM, we have long-lasting transient absorption, which shows that indeed charge separation takes place, and charge separation takes place on carbon nanotubes because we have bleaching of the carbon nanotube band.
Okay, so we have no time. Thank you again.
Thank you.
And next talk will be presented by Dr. Sergei Yakunin from Switzerland. Optical amplification and lasing from compact films of perovskite nanocrystals.
Thank you, Mr. Chairman, for kind introduction. And of course, I would like to thank conference organizers for giving me opportunity to give a plenary talk. And today I would like to speak about optical gain effects and lasing in medium of perovskite nanocrystals. And before going to scientific part of my talk, I would like to introduce our group. So this is a group of around 30 people at chemistry department of ETH of Zurich, and this group is led by Professor Maxim Kovlenko, and mostly we have a lot of chemists who are providing quite novel and beautiful materials, and we have also a few physicists, my colleagues, who are trying to make some kind of preliminary characterization and invention of new devices based on these magic materials. And here I listed people with red who are actually either providing me materials or helping me with characterization for this work, which I want to present. Here I also mentioned some scientific forms which we would like to acknowledge, and also just few companies, the only few which I'm allowed to show. I would also like to thank those people and companies for providing us financial support. And now I would like to make a short introduction what is this class of novel materials. This is solution processed semiconductors. This is lead halide perovskite. They have such cubic crystallographic structure, which with general formula similar to their oxide perovskite analogs. And in this formula, the last element, it plays a role of anion, and typically we work with halides, and changing such halides like chloride, bromide, and iodide, we can broadly tune band gap of this semiconductor material. And then another very important part of this material, this is metal ion. Normally we work with lead, and also we work with some less toxic materials as well. But this ion plays very important role because molecular orbitals of this central metal ion provide outstanding electronic coupling, and that's why charge transport. And then cation part, which is a bit less important, and this can be either monovalent organic cation, or it can be also metal ion. And mostly this cation part respond for chemical or morphological stability of such material. And then a bit of history of perovskites. First, this material was discovered half of the century ago. These were a couple of papers in Nature, and I want to highlight your attention. These are not abstract. This is the full length of the paper. And these two papers actually opened history of perovskites. They show just basic elements of synthesis and very basic optoelectronic properties. And then for about 50 years, these materials were almost fully forgotten. And then they were somehow rediscovered only in 2009, when people from dye-sensitized solar cell field, they tried to use this perovskite metal halide perovskites as a synthesizer for infrared range for their solar cell. And they, in principle, already got pretty interesting values, around 5–6% of power conversion efficiency. And then during optimization process, it was a very funny story that simply when they throw away all of the standard active material as organic dye, and then they leave only this perovskite semiconductor inside solar cell, they greatly jump in power conversion efficiency for about 2 times, and they reach about from 9 to 11%. And they were two really really famous two papers which opened era of perovskite solar cell. And now this graph is the best illustration why these perovskite materials are so important and why they took so much attention. Actually, what I heard, nowadays this is the most cited material in the literature, because before it was graphene and two-dimensional materials, and nowadays it's perovskite. So if you look, this is like a starting point of record for power conversion efficiency, and just with couple of years, this power conversion efficiency almost doubled and reaching now 22%, and really competing with silicon solar cells, which are the main material now in solar cell industry. And now I would like to present what is just our our field in this perovskite story. So in 2014, actually our group was pioneers in invention of highly luminescent perovskite nanocrystals. And then a couple of years after, we start to grow a single crystal of perovskite and try to make devices out of them. And we are also quite desperate in looking of new perovskite structures, playing with 0D, 1D, 2D, up to 3D materials. And this is not about quantum dots, nanowires, or thin films. This dimensionality, it's about crystallographic structure and direction of electronic coupling in such crystals. And then what we are also interested in to make heterostructures, combining such perovskite nanocrystal together with other functional materials in order to improve their stability and optoelectronic properties. And now this is about devices. So actually our group, we do almost everything except of solar cell. So we don't do mainstream business, but with the rest, what we are doing, we almost in many cases worldwide leaders. So here, actually we were pioneers opening the field of solution processed perovskite hard radiation detectors, starting from X-rays, nowadays working with gamma rays and neutrons. Then we were for the first time found optical gain effects in compact film of perovskite nanocrystals. And then we also, this is our recent invention, this is a demonstration of full color pixelated detectors where perovskite layers are stacked all together. My really big personal disaster when we were already working with perovskite and optical amplification, and then at the morning you come to the work and you read a paper when they are already reporting some kind of similar effects, but with materials with a bit different morphology. But it was also still painful. So actually, the first optical amplified spontaneous emission in perovskite thin film were reported in 2014 in this paper. And what amplified spontaneous emission is? Most of the people probably in this auditory would know, but just in order to explain everything, I would like to mention that amplified spontaneous emission is just one step towards almost a laser. So it's simply like a laser where you remove a resonator. So actually it's demonstrating ability of material to make optical gain inside. And how it looks like. So actually initially at low pumping intensity, you just observe a photoluminescent curve, and just after certain threshold in intensity, very narrow and sharp line appears. And this line, this is already like a partially coherent emission, showing the region where you have optical gain effects. And another way to prove that this amplified spontaneous emission, where you observe photoluminescence lifetime, you see drastic acceleration of this lifetime after threshold of optical gain. In perovskite, these optical gain effects start at, in principle, quite low threshold, which show very great potential of this material for laser application. And another very cool ability of this material that you can almost continuously tune, so actually not almost, but really continuously tune through the whole visible range, just playing with halide composition, as I told in previous slide. And then, in principle, gaining from the perfect cubic structure, crystallographic structure, and from the fact that these materials, under certain conditions, they would like to grow as very tiny and very perfect nanowires. Actually, they can work as perfect waveguide Fabry-Perot resonator. And combining also the optical amplification effects, what people observed with this paper, that you can make already pretty nice nanoscale lasers with very low thresholds of optical pumping. Again, you see these effects of acceleration of the lifetime, and on this photo you see that emission is directed from the edges of the resonators, from the edges of nanowires. And then it's already our work. As I mentioned, we started to cook by hot injection colloidal chemistry, pretty nice cubically shaped due to cubical crystallographic structure, and very monodisperse perovskite nanocrystal, and they are quite unique in properties. So first of all, they have very high optical absorbance, reaching values about 10 to the power 5 inverse centimeters, which is pretty high. And then they have very narrow optical emission with very high quantum yield, reaching almost 90% in quantum efficiency. And this emission, this narrow emission, can be also tuned continuously through the whole visible range. And if you look, if you now plot this emission spectra on a gamut curve as a points indicating certain colors, you see that they are really close to the edge. And this fact that they are very close to the edge, it shows that the color purity in this material is really outstanding. So actually, if it just takes 3 spots of perovskite, of emission of perovskite nanocrystal with different composition, and when we make like area of this gamut coloring, it already shows like 140, more than 140% of existing NTSC television standard, and it's also a bit higher than the next television standard which will come into in 2020, in 2020 year. That's why it was really great interest for this material as an application for emissive material. And then, in order to highlight the interest to this paper, for a couple of years after publishing now, it's around 1,200 citations, what this paper has. And another very cool feature of this material is that actually after cooking, you can still modify optoelectronic properties. So actually, it has ability for anion exchange. So actually, this halide composition you can change after the synthesis. So in principle, in solution of in colloidal solution of perovskites, so actually it should be video, but I think it will not work in this case. Maybe not. But just believe me. So here is a it was a demonstration where in solution of colloidal perovskite nanocrystals, where you add precursor containing high concentration of other halide, and simply it will change color within few seconds. Another feature of this material is, so actually the same demonstration of the same feature of anion exchange, that if you mix a few different types of perovskite nanocrystal with different halide composition, they will interexchange their galides, and they will come up with just one common color. It makes actually very big trouble for people who are trying to apply this material for solid state lighting, trying to combine this material in order to make very broad white light emission. So they would need to encapsulate these materials. And another interesting interesting example how we can play with this material, that we can combine this one, so we can put this perovskite nanocrystal inside mesoporous silica. And that's why it starts to be encapsulated, and this material now you can, so here you can actually almost totally block this anion exchange. And now I would like to come to optical gain. So actually for us it was, of course, a very big challenge to get it. So it took us a couple of months before we understand that actually in order to get such amplified spontaneous emission effect, we really need to make very compact films of nanocrystals. Afterwards, we understand that actually one of the critical condition for optical gain is that nanocrystals should provide coupling of their excitons. So actually these lasing effects and optical gains, we believe that it appears due to biexcitonic, or other people call it biomolecular recombination and emission. And here in thin film of perovskite nanocrystals, where thickness is enough to make some kinds of waveguide geometry, we see this very narrow, tiny spectral feature with very low threshold, where we also see this effect of drastic acceleration of the lifetime when we slightly increase pump intensity. So this is actually the all necessary proofs that you have optical gain. And then what we also demonstrated that these optical gain effects actually you can tune through the whole visible range. Just when we plot the threshold chart, you can see that actually the lowest threshold we got from for green material, whereas for blue and for red ranges they have slightly higher thresholds. We also measured optical gain coefficient, which shows quite high values of 450 inverse centimeters, which is one of the highest values in between semiconductors. And then we also tried to go, so first we started with very short excitation pulses in femtosecond range, and then we tried to go to longer excitation pulses, trying to reach some kind of continuous wavelengths or quasi-continuous wavelengths range, which is highly demanding now in order to get low or threshold less lasers. And actually what we reached 10 nanoseconds, which is already faster than this build-up time of amplified spontaneous emission. It shows that in principle we already worked with quasi-continuous amplification regime. Then of course we were interested, what about lasers? And very simple and easy way to make optical resonator would be to use just silica microspheres. So we took these microspheres and then we conformally covered these microspheres with thin layer of perovskite nanocrystal, and after optical pumping we see that they show already nice effect of whispering gallery modes, which looks like equidistance mode of lasing, which shows certain threshold. And playing with the size of microsphere, we can also vary the distance in between those modes. Again, whispering gallery mode effect we observed in microcrystal of perovskite, and we observed certain lasing effects also just in thin film without any resonator. This lasing effect also quite known as random lasing, or effects when you see on a single shot spectrum chaotic positioning of sharp lasing lines, and they do not appear. So actually any new pump shot, they will show quite different mode structure. And this is a very modern direction where people expect bright future of this application for security and cryptography. But we are mostly a group who oriented on chemistry. That's why we have a lot of people who providing different materials, and we were really interested to play with different chemical composition and different morphology of perovskites. And this is another good example when we try to work with methylammonium cation and with methylammonium lead bromide thin nanoplatelets. And due to such specific morphologies, they have a tendency to make such kind of very long aggregates already inside liquid solution. So actually, in liquid, they form already such kind of needles. And of course, it makes quite good benefit for electronic coupling of excitons already inside these long wires. And of course, it makes good coupling for thin film. So actually, some effects of optical gain we already observed in solution, where we see strong acceleration of the lifetime under increasing of pumping intensity, which is pretty similar to the effects what we have in complex film of these aggregates. And due to this better coupling, we have actually lower threshold. Then we were interested to work with another type of cation, which is again organic type of organic ions, which is formamidinium, which in certain cases provide better chemical and morphological stability. And we also demonstrate that this material will show optical gain for green emission when anion is bromide. And we also worked quite a lot with iodides, which makes the narrowest band gap possible for those perovskites. So actually, as you remember from previous slide, we have certain problems that we have very high ASC threshold, and we actually did not reach near infrared range. We had really higher thresholds for in red range, but due to the ability of those nanocrystals to merge together under thermal treatment, they start to merge in thin film, and it also improves better exciton coupling in such film. And then we have a really big drop in optical gain threshold. So those films, they show really nice effect for optical gain. And what we also observed for such material due to this merging of nanocrystals, that we start to observe electrical transport in such material, and which we show in photoconductivity effects. So this material would also work as a photodetector, which is very important. I will show you a couple of slides later. So we also worked, with surface chemistry in order to find such very short ligands for these nanocrystals in order to make intrinsically compact films already without any kind of additional washing or other kind of ligand exchange. So we found such kind of very, very nice ligands, which shows pretty good properties, providing even lower threshold for optical gain. And those ligands were actually also very good for electrical transport in these layers. So, and they were also beneficial for making LEDs. And now I think it's already good to go to conclusion. So actually what I mentioned, that these solution process perovskite nanocrystals, they are really promising materials for optoelectronic applications such as light emission, LED lasers, and photodetectors. And their benefits, they come from facts of high optical absorbance, really bright emission. Nowadays, people reaching almost 100% of PL quantum efficiency for such nanocrystals. And another very important technological factors it's a cheap production and deposition for such materials. And the last but not least, it's a possibility for very flexible band gap engineering. So combination of those properties give us a chance to expect in future even electrically pumped due to this outstanding charge transport and high emission property, even electrically pumped lasers in future. And I would like to thank you for attention, and with my last slide to make a short advertisement for highly motivated and highly skilled master, PhD and postdoc students for possibility of couple of months for internship in our group working with some material science projects. Yeah, so thank you for your attention.
Thank you. Question, please.
Maybe you can tell several words about the programs for electrically pumped lasers.
There actually there are many problems. First of all, it's not fully demonstrated that colloidal quantum dots, if they're really able for continuous wavelengths pumping operation, which is like a one step in between towards these electrically pumped lasers. So there are some recent publications where the people show that they claim that they have this optical gain for CW pumping, and people also try to extrapolate in which conditions it would be possible to reach electrically pumped. So in principle, for very optimistic estimation, there are few orders of gap in between power density which you still need to improve that for thermal stability of this material. So if in future we would find the way how to make heat transfer better and threshold for optical gain lower, in principle there is like around few or two orders of magnitude distance towards this dream.
Okay. Other question?
The perovskites particles have also some disadvantages, like very low stability, yes? And bad stability. Have you some concepts?
So you mean chemical stability?
Yes.
So actually it was partially true for really first attempts to grow them, where their stability was around couple of months. So nowadays people made, and actually our group was really a leader in this direction, where we really improved condition of the synthesis and surface chemistry of these nanoparticles, where in principle stability of those nanoparticles we have at least years what we have in the lab. And these materials I just recently saw in the internet that there are commercially available samples of this exactly of the same nanoparticles, where companies provide at least, and they claim that it would be at least few months of stability. So actually in the lab, in our group, we have much more better stability. I would say that stability is not the main issue for this material.
Okay, and I would like to ask some, not concerning physics, but ecology. As I know, lead is from 2011 is forbidden to use.
Actually, it's just partially true, because there are now such kind of ROHS compliance, which is certain limitation in amount of lead in your final product.
100 ppm.
Yeah. So actually, estimation of our industrial collaborators that content of lead in TV display would be about one order less than this ROH compliance, and they have like a joke. So actually, your TV, your big TV screen would contain LED much more less than a box, than a paper box in which this TV would be delivered. So there is formally, this material is lead containing. We are working hard in order to find some kind of alternatives for less toxic materials. It's really big challenge. But from the point of view of toxicity, we are fully agree and fully compliant with ROC's requirements.
Okay, so thank you again. It was a very interesting talk. And next talk, I would like to invite Professor Oleg Dmitriev from Ukraine, delayed energy transfer between J aggregates of some dyes.
Good afternoon, and first of all, I would like to thank organizing committee for providing opportunity to present my results. I will speak about energy transfer in large aggregates. And first of all, energy transfer is an important issue which can be found in different fields like physics, biology, chemistry, and particularly important application of this phenomena can be found in photosynthesis of green plants, for example, in artificial solar cells or in photochemical reactions. So I will speak about specific of energy transfer in G aggregates. And first of all, I would like to I will give an introduction to the energy transfer mechanism, and then I will discuss original results about efficiency of energy transfer in G aggregates, and energy transfer routes in G aggregates, and control of energy transfer between G aggregates, and then I will conclude. So it is well known that energy transfer can take place mainly by two mechanisms, radiative and non-radiative. A main difference between this mechanism is the distance between a donor of energy and acceptor of energy. For example, if we have a relatively large distance between donor and acceptor, which is higher than the wavelengths which emits the donor, then we have the so-called far-field case when energy can be transferred only by a radiative way. And if we have a relatively small distance between donor and acceptor of energy, we can transfer energy by non-radiative way. So in a radiative mechanism of energy transfer, we have a large distance, as I said, and in this mechanism, we have simple relaxation of the donor of energy when the electron relaxes to the ground state and emits photon, which is absorbed by the acceptor of energy. So we have a simple reabsorption process in this case. In non-radiative mechanism, we have two main routes. The first route is Forster resonance energy transfer, and the second one is the Dexter double electron exchange, which again are different by the distance. For the Forster dipole-dipole interaction, we should have distance of about less than 10 nanometers. And for Dexter double electron exchange, we have practically physical contact between donor and acceptor, where the donor transfer electron, excited electron is transferred to the acceptor, and acceptor provides a ground state electron to the donor. So I will speak about only the first resonance energy transfer, because I will consider molecules which are at not in the physical contact, but at some contact from each other. What is more important for the first resonance energy transfer, that in this case we do not have transfer of a real photon. In this process, when the donor is excited, dipole is excited, it immediately induces excitation of the acceptor. So this process is very fast. It proceeds during few picoseconds or even less. And the efficiency or the energy transfer rate can be described by this expression. So the rate is inversely proportional to the distance in the 6th power. There are a few conditions for the efficient energy transfer in the first resonance process. The first condition is the overlap of the emission band of the donor and the absorption band of the acceptor. The second condition is the close physical proximity, donor-acceptor distance between players of this process. And the third condition is alignment of dipole moments. The dipole should be aligned in order to efficiently transfer the energy. So the efficiency of energy transfer in the first process can be described by these simple expressions. First expressions is based on the ratio of intensity of emission of the donor in the absence and in the presence of the acceptor. So this is an energetic relationship. And the second expression is based on the lifetime of donor in the absence and in the presence of the acceptor. So in principle, these expressions should be equivalent. They should give the same results if we deal with the first resonance energy transfer. In large aggregates, there is some specific because the size of aggregates can be comparable with the distance between the aggregates. In this case, the point dipole approximation cannot be applied to this situation, and we should consider each aggregate as a set of different dipoles which interact so each dipole on the donor aggregate will interact with every dipole on the acceptor aggregate. That means that there are many channels through which the energy can be transferred. For example, if we have the dark state here, when dipoles are antiparallel, energy cannot be transferred between these dipoles. Energy can be transferred from the other dipoles to this point. And that means that in large G aggregates, we have a specific situation when energy can be transferred through additional channels, and energy can be transferred more fast than Forster theory describes. So this example represents the energy transfer between in propyl bacteria when we have energy transfer from one band to the other, and it proceeds much faster than the Forster resonance theory predicts. This is the calculated rate of energy transfer for Forster theory, and this is a real experimental results. For large aggregates, we have two important conclusions. The first one is that there is a faster energy transfer rate using additional channels in large G aggregates, and the second conclusion is that the energy transfer can proceed faster than single exponential decay. Again, because we have different channels through which the energy can be transferred. So I will consider large aggregates based on specific molecules. For example, these lone molecules, which are polar molecules and which can form so-called G aggregates. So in principle, G aggregates can be composed of dozens or even hundreds of molecules, which just have nanometer or even micrometer sizes. But when we excite exciton in these G aggregates, we can excite at least several molecules concurrently. They will be excited in the same phase. And this is the specific of exciton in G aggregates. Because this exciton has high energy and it can migrate along the G aggregate ensemble. We studied two specific molecules, thiamonomethyl cyanide dyes, which have a similar structure and which are different by only end groups. And this specific structure provides that the optical properties, absorption and photoluminescence spectra of this species are very close, shown here. And for example, this structure provides the fact that the emission of the donor molecule overlaps very well with the so in films we compared photoluminescence properties of the films prepared from the neat components and from the mixture of donor and acceptor aggregates. So we can see that a spectra of films provide a good overlap of the emission of G aggregates of the donor molecules and absorption of acceptor G aggregates. And this effect provides a good energy transfer. So we can see that in the emission of the absorption increases very strongly in the presence of the donor by a factor of more than 3. And what is specific for this case that the shape of the acceptor aggregates is practically the same when we enhance the emission of acceptor G aggregates in the presence of the donor. The shape becomes almost the same, and the donor emission almost completely quenched here. So we can calculate the efficiency of the exciton energy transfer to be almost 100% in solid films of a mixture of donor and acceptor G aggregates. And this process also is very fast, less than 20 picoseconds, which was the limit of our measurement device. So we can conclude that in this case, the energy transfer proceeds by the Foster energy mechanism. In solutions, the situation is some different. So again, we have a good overlap of the emission of the donor G aggregates and absorption of acceptor G aggregates here, which provides again a very high enhancement of photoluminescence of acceptor in the presence of the donor G aggregates. This enhancement is anomalously high because in terms of energy, if we calculate the area under the curves, we can find that the area under the green curves even exceeds the sum of areas under the blue and red curves. So, and in addition, we can observe that the shape of the enhanced emission is different from the neat photoluminescence of acceptor G aggregates. That means that something happens in solution when we add donor molecules to the acceptor G aggregates. Something happens in the solution. When we measure the decay of photoluminescence of donor in the absence and in the presence of the acceptor, we can find that the decay curve is almost the same. So we didn't observe any significant change of lifetime of the donor in the presence of the acceptor. And in principle, we can describe the decay function as a B exponential decay, and both components, both time components change, but this changing is not significant, is not typical for the first-order mechanism of energy transfer. And if we calculate the efficiency of energy transfer based on the change of lifetime of the donor, we get only 5% of efficiency for energy transfer, which is quite different from what we had from evaluation of energy transfer from the comparison of intensity of photoluminescence. So, and if we look into the other components of emission of the acceptor in the of donor aggregates in the presence of the acceptor, we can see a quite big difference. So the many components become a lifetime of many components not only changed but became even increases. That means that energy transfer is significantly delayed in this process, in the solution. So we have interim conclusions that we have effective energy transfer based on the evaluation of intensity change. But we have delayed energy transfer due to the increased lifetime of donor components in the solution in the presence of the acceptor. And these results cannot be described by the first-order energy transfer theory. You can ask me that this can be done by radiative energy transfer, but we made special experiment which rules out this possibility, because when we directly illuminate solution of the acceptor G aggregates with the wavelengths which is the same as the wavelengths of the donor emission, we did not observe any enhancement of the acceptor photoluminescence. So the spectrum is very emission is very low here. I should mention that solutions have some specific. First specific is that G aggregates are in the equilibrium with the dimers in the solution. So in solution we have not only G aggregates but also monomers and dimers, and G aggregates increase its length due to the addition of dimers to the body of to this ensemble. So, and we can control this process, for example, by illumination of by specific wavelengths of the solution. If we illuminate the solution by wavelengths which is absorbed by G aggregates, we can increase the dimer components in the solution. And when we illuminate solution by which is absorbed by dimer, we can increase the G aggregate component in the solution. So we have equilibrium which can be changed in the solution. Moreover, emission, photoluminescence emission of G aggregates has a multi-component, have many components, several components. We can decompose the emission spectrum in at least 4 components which correspond to free resonance exciton emission, self-trapped exciton emission, dimer emission, and excimer emission. So these components are illustrated schematically in this picture. When we have G aggregate, when we have excitation of free exciton, this free exciton can be relaxed through interaction with vibronic modes and give a self-trapped exciton, or it can diffuse to specific sites where this exciton interacts with the dimer species and creates excimer emission. The same situation is typical for the acceptor G aggregates. We have several components, and each component has specific lifetime, shown here. The most rapid component is, of course, free resonance exciton, and the most slow component is excimer component here. So, in order to explain the mechanism of energy transfer in the solution, we performed experiment with increasing concentration of donor or acceptor. So, this case describes increasing concentration of acceptor when a donor concentration is constant. Here, solid curves correspond to the mixed solution, and curves with symbols, with circles, correspond to the neat acceptor solution. And what we can see here, we can see that in the mixed solution, the contribution of the donor G aggregates significantly reduces because they give up the energy to the acceptors. But excimer emission also decreases in the mixed solution. For example, you can compare these yellow curves. Excimer emission in the mixed solution is significantly lower than in the neat acceptor solution. And what we can do here, we can subtract the emission of a neat acceptor species from the spectrum of mixed solution, and if the contribution of the components is simple additive, we should get, in principle, we should get a photoluminescence spectrum of the donor independent of the concentration of the acceptor. But if something happens in the solution, then the spectrum of the donor will be changed, of course. And this is illustrated here. We can see a spectrum of the donor emission and spectrum of the donor emission in the presence of the acceptor when molar ratio is 1:1. So we can see the quenching of the donor G aggregates and increase of the acceptor G aggregates. So energy is transferred from G aggregate, donor G aggregate to acceptor G aggregates, which is quite understandable. But when we increase concentration of acceptor more in the solution, we have a qualitative change in this picture, because we observe that we have a main contribution, which main enhancement of the spectrum is located near 550 nanometers, which does not correspond neither to G aggregates of acceptor or dimer of acceptor. So in this picture, we see that this enhancement is due to the quenching of the donor G aggregates here, and then at high concentration, we observe also quenching of G aggregates of the acceptor. And also we observe less contribution of excimer in the mixed solution, as I showed you before. So the second case, when we increase concentration of donor in the solution with a constant concentration of the acceptor. So again, we have contribution of XMR in the neat donor solution much higher than in the mixed solutions. That means that the XMR become not so effective in the mixed solution. And this is again demonstrated by the difference spectrum when we subtract the neat donor spectrum, photoluminescence spectrum of the donor from the photoluminescence spectrum of the mixed solution. Again, here we have a rapid decrease of G aggregate emission of the donor. So because they provide energy for the mixed solution for the acceptors, and we see the decreased contribution of the XMR, and we see again the increase of the increase of energy in the range of at the wavelengths of approximately 530 nanometers, which again doesn't correspond neither to G aggregates or dimers of G aggregates in the solution. So. So we observe, if we look at different components of the mixed solution, we observe the delay of energy, delay of lifetimes. For example, delay of lifetimes of donor in the presence of the acceptor, as I told you before. And also we observed also the significant delay of lifetime of G aggregates of the acceptor. That means that in the mixed solution we have something new, something different from the pure G aggregates. And what is the reason of this delayed energy transfer? In principle, we have a dilemma. We have very efficient energy transfer, but this energy transfer is delayed. So we can find the analogy of the energy transfer, for example, in the relay race when the athletes transfer the baton, and this is analog of energy transfer. And of course, there are certain recommendations how to transfer baton very efficiently without losses. And the difference between these pictures is not only the historical perspective, but also the fact that about 1 century ago, the speed of the athletes were certainly lower than in the modern world. And we can think that with lower speed, the efficiency of transfer of baton was more reliable than in this case, where the athletes were very quick and they lost the baton here. So coming back to our results, we can describe the mechanism of energy transfer by the delayed process. The delayed process is due to the diffusion of the exciton to the specific sites, where the energy can be transferred to the other species. For example, if we have a pure donor solution, we have energy transfer to dimers, and we have an XMR excitation here. But if we have a mixed solution, there is a competition between XMR and Xplex formation, where the foreign species can interact with the sites and give Xplex formation. So This exciplex formation is also accompanied by the rise. In order to form the exciplex, the exciton should have some time for the diffusion to the specific sites. And we really observed this rise time, which was about 70 picoseconds. So we can describe the energy transfer processes in the mixed solution by different equations, which represent formation of excimers, simple exciton energy transfer from the donor G aggregate to the acceptor, and finally formation of exciplex when the energy of G aggregates of the donor is transferred to some species of the acceptor molecules. And the similar process can also be described when we excite acceptor G aggregates, which also can transfer energy to donor species and form exciplex of the other type. In conclusion, I tried to show you that for large aggregates, G aggregates, we have a fail of the point dipole approximation. We have anomalously high efficiency of energy transfer, and we have anomalously slow energy transfer in solution. These two anomalies can be explained by exciplex formation. And this exciplex arises due to the diffusion of free exciton to specific sites, where it competes with formation of excimers. Finally, I would like to thank my co-authors, Dr. Piratensky, who helped with time resolve measurements, and Dr. Slominsky, who synthesized the dyes. I would like to thank partial support of State Fund for Fundamental Research, and thank you for your attention.
Thank you. Unfortunately, we have time only for one very short question, please.
If we say about the cluster energy transfer and energy study, investigation, to clear up all the processes, one should prepare the special conditions when you excite the donor only and not excite the acceptors. In your case, you excite both donor acceptors and all your species in the solution. Why don't you make more simple system, because I really have enough.
Okay, you mean that we can excite a donor?
You don't show any excitation wave on your pictures, but you excite both acceptors, which absorption is on the blue side corresponding to the donor absorption. And but for the pure cluster energy transfer investigation, we should not excite acceptor on this experiment.
Yeah, but I think that this is not possible, or at least hardly possible, because when we excite donor, excitation.
Please use microphone.
When we excite donor molecules, in principle there is a tight overlap of the spectra, and in principle it is very difficult to separate excitation of the donor and the acceptor in this case.
Okay, so thank you again for the very interesting talk. And next talk is will be presented by Professor Zbigniew Lesnikowski from Poland, application of boron clustered in nanoconstruction, present and future.
Mr. Chairman, ladies and gentlemen. It is a pleasure to be a part of this meeting held in beautiful city of Kiev. Some of you may wonder why a person from the Institute of Medical Biology and from the Laboratory of Molecular Biology is talking about boron clusters. So let me introduce myself in a few words. I'm a chemist, and more specifically a nucleic acid chemist. We are working in multidisciplinary research on the junction of biological chemistry, inorganic chemistry, medicinal chemistry, and molecular medical diagnostics. Since many years, we are interested in using of unique properties of boron clusters for modification of biomolecules. So we work on development of methods for the synthesis of this kind of composites. We study the properties, physicochemical and biological, and we look for the possible practical applications. Boron clusters are quite exotic molecules, even for most of chemists. So I will start from a short introduction. Also, the topic of my presentation, boron clusters, nanoconstruction, present, future, is quite broad. Therefore, I will focus only on some issues with the hope that it may attract you to the boron cluster fields. The story on boron clusters starts in 50s of 20th century, and for the work on boron clusters and in general on boron hydrides. Boron clusters belong to the boron hydrides class of compounds. 2 Nobel Prizes were awarded, one for Herbert Brown and another for the William Lipscomb. In spite that the research on boron clusters started in the 50s, for the next more than 10 years, no papers on the chemistry of this class of compounds appeared in open literature. It is therefore that the research on boron cluster was initiated for the military purposes and the military applications as high energy fuels for aircrafts and rockets. But in the 60s, in the beginning, or actually in the middle of 60s, these projects, which were going on as well in the United States as in the Soviet Union, were abandoned, and the research on boron clusters moved from the military laboratories to the academia. But the huge stocks of boron compounds, boron clusters, remained, and as a matter of truth, they formed quite a convenient base for the development of research on boron clusters. Boron clusters are a huge family of compounds. The size of boron clusters range from 3 boron atoms up to more than 20 atoms in one cluster. They also can accommodate several heteroatoms in the cage molecule. On the slide are shown some representative examples of boron clusters, which are most often used in medicinal chemistry and also in nanotechnology applications. The best known molecule, it is, sorry. The best known molecule is a dodecaborate anion, which contains 12. Yeah. Yes. The best known example of boron clusters is dodecaborate anion, which contains 12 boron atoms and 12 hydrogen atoms linked to the borons. The boron BH groups in such a cluster can be replaced by the various heteroatoms, very often by carbons, and after replacement of two BH groups by two CH groups, dodecaborane are obtained. They exist in three different isomers, depending upon the mutual location of carbon atoms. This is a meta, ortho, meta, para isomer, and they differ in properties. Boron clusters are very good ligands for metals. And they, after coordination of metals, they form metallocarbonanes. The example is shown here. It is again a huge class of compounds with various applications. On the picture, there is Fred Hawthorne, the discoverer of metallocarbonanes and one of the founding fathers of metallocarbonane chemistry. Here there is a basic of carbonane chemistry. The original method for the synthesis of dodecaboranes was the reaction of decaborane with a triple bond of alkenes. This method is very useful and is still used. Very important and very useful property of carbonanes is deboronation. Removal of one BH group from electrically neutral closed chlorocarborane, and transformation into negatively charged nidocarborane. And just this molecule, this kind of molecules, because it is only an example, are very good ligands for metals, giving the rise to the metallocarbonanes. This type of complexes, coordinated compounds, can accommodate almost all metals available in periodic table of metals, which increase the potential of this kind of molecules. Some properties of carbonanes and metallocarbonanes which are useful for the practical applications are shown on this slide. The spherical or ellipsoidal rigid geometry provide a platform for molecular construction in 3 dimensions. They are the hydrogen atoms connected with borons are hydric, which means that they have a partial negative charge. They can be lipophilic, amphiphilic, or hydrophilic, depending upon the type of the boron cluster and the substituents attached to the boron cluster scaffold. They are chemically stable, but simultaneously susceptible to derivatization. They are resistant to ionizing radiation, which allowed to use this type of molecules, actually derivatives of metallocarbonanes, as extractants for the purification of nuclear waste from the nuclear powers. They also, the high boron contents is characteristic for these molecules, and this is important for some other applications, for example, as boron carriers for boron neutron capture therapy of tumors. Some applications of boron clusters based on this and many other properties which are not, were not mentioned are shown on this slide. We are most interested in medicinal chemistry applications and more recently in nano science. But as you see, there are a range of different possible applications of this type of molecules. The field of nanotechnology can be roughly divided in two areas, nanomaterials and nano devices. I will give some examples of application of boron clusters in both areas. It's about nano devices. The first nanocars, the molecules able to move on the surface, were built of fullerenes. But the chemistry of fullerenes is not easy, and synthesis of this kind of structure took 14 steps, and the overall yield was 1% only. It was soon realized that boron clusters, like for example paracarborane shown here, are more convenient because the chemistry of boron clusters was in that time much better developed. So this kind of molecule or molecular car, nanocar, was synthesized in 2006. To move these molecules on the surface, different kind of processes are used and different molecular engines. One example is shown here, and it makes use of changing of conformation of the molecule under the influence of external stimuli, in this case irradiation with UV light. Another example of nano device based on boron cluster structure are Nano Rotors made of metallocarbonates. Actually, all metallocarbonates can rotate around the axis, but the efficacy and the energy of such a motion depends upon the metal coordinated by the boron clusters. It was found that the complex of nickel gives best results because the rotation, controlled rotation, can be achieved by changing the oxidation state of nickel from +3 to +4 and the reverse from +4 to +3. And this is connected with the changing of the conformation of the molecule. One can ask what is the use of this type of structure. Here is an example. If bulky substituents are attached to the ligands, one can, changing the conformation of such a molecule, one can build a nano valve, which can be opened in one conformation and be closed in another conformation after, as I said, external stimuli. This kind of devices add to the tools, to the toolbox of molecular structures, which can be used for the construction of more complex devices. This is another example. In this case, it is a material. A search for the materials which efficiently can storage hydrogen is very important. It was found that this kind of nanostructures are very efficient in storage of hydrogen, and depending upon the size of this space, also a methane. Another application of boron clusters is to modify the properties of metal surfaces. The easiest case is to modify the surface of the gold nanoparticles with boron clusters containing thiolo, function because the formation of the stable bond between the sulfur and gold. And again, using a different boron clusters with different properties, more or less lipophilic, for example, or containing additional substituents attached to the boron clusters, one can modify the properties of the metal for different applications. Now I am moving to the nucleic acids, and in the next few slides I will show how we made together nucleic acids and boron clusters. Since the discovery of nucleic acid structures in the 50s by the Watson and Crick, the DNA was recognized as a most important biomolecule, called even the molecule of life. But since at least 2 decades, DNA is studied not only for the biological applications, but also for the technical applications as a material in nanoconstruction. And it is used not only as a molecule of life, but also as a molecular wire. And some advantages of DNA as construction material for nanotechnology are shown here. The most important, actually, property is the capability to self-organization due to the specific interaction between nucleobases according to the Watson-Crick rules. But nucleic acids are at present easily available thanks to the methods of automatic synthesis of chemical synthesis of nucleic acids using automatic DNA synthesizers. They are also applicable. They are also available due to the amplification by the enzymatic methods. They are susceptible to chemical modification. What is important, nucleic acid can store, transmit, and process information. They are able to transfer electric charge, and some nucleic acids also have catalytic activities, and they have enzymatic properties. The nanotechnology of nucleic acid is a huge, broad field. Some examples are shown here, and I am not going into discussing details of this slide, but I would like to mention few reasons why we decided to approach construction of the new type of building blocks for bionanotechnology based on boron clusters and nucleic acids. So icosahedral carborines possess a unique geometry inaccessible in organic chemistry, then can be used as a platform for positioning of substituents, in this case nucleic acid substituents, in a specific way in space. It also, this kind of constructs also allow to incorporate into nucleic acids and further into nanoconstructs properties which are not available in the case of unmodified nucleic acids, but can be incorporated together with the unique properties of boron clusters. And in addition, using as a scaffold or building core the rotating metallocarborines, one can construct a dynamic DNA nanostructures based on metallocarborine molecular rotors. We envisioned that using this approach, one can synthesize, for example, this kind of the molecule. And on the next few slides, I will show you how this vision became the reality. So So first, we synthesized chemically a system containing boron cluster, a substituent which allows attachment of this boron cluster to the solid support which is used in automatic DNA synthesis. There are also two linkers allowing to attach nucleic acids in these positions. Then this intermediate was attached to the solid support, and the automatic DNA synthesis was performed using the DNA synthesizer. Here is a simple example shown with oligothymidyllic acid attached, but we also synthesized this type of structures, which we called dipods, because these two oligonucleic acid substituents with so-called heterooligonucleotides. We also synthesized another set of molecules of this kind, but with nucleic acid sequence which is complementary to the first one. And these two building blocks were mixed, and they formed nanostructures were studied by several methods, using high pressure liquid chromatography, using capillary electrophoresis, also atomic force microscopy, and also cryo electron microscopy. And the pictures which are shown here are just obtained from the electron microscopy. And as you can see, structures with a defined topology are formed. In this case, there are 8 dipod units forming a cycle. The work on the synthesis of building blocks containing not only 2 but 3 nucleic acids are ongoing in our laboratory, and this type of building blocks, we hope, will allow for the synthesis obtaining for the construction not only 2-dimensional nano structures of this kind, but also 3-dimensional structures. We also work on using of this kind of nanostructures as carriers for therapeutic nucleic acids to improve the delivery into the cells. Of course, there are many other possible potential applications of this type of molecules. So, in summary, boron clusters offer a new opening toward design of innovative nanomaterials of different types. They provide not only a versatile platform for molecular construction in 3 dimensions, but allow also for incorporation into nanostructures the unique properties of boron clusters. And I think that this is very, very important feature of this type of new building blocks. I wish to thank my co-workers, chemists. There are also several biologists in my laboratory, Sławek Janczak and Ola Rembowska. The work is performed in collaboration with Professor Barbara Nawrot from the Center of Molecular and Macromolecular Sciences, and her co-workers, Damian Kanowski, Katarzyna Olbińska, Katarzyna Kulik. And the work is supported financially by the Polish Ministry of Science and Higher Education within the grant of composites of nucleic acids and oligofunctionalized boron cluster as new material for bio-nanotechnology. And I wish to thank for your kind attention.
Thank you very much for the very interesting talk. So we have a couple of minutes for discussion, please.
Can you show me the last picture? Oh, the last one.
Next.
Yes. Yeah, please.
Yes.
So we have that reconstruction and we have this picture. But can you tell me what is in the center?
Inside.
What is around?
Colleagues with whom we collaborate and with whom this analysis was made, that this kind of halo, it is due to the, I would say, a movement of the molecule which decreased the overall resolution of the picture. So the real nano construct, it is this.
Yes.
And this is a halo around the this nanomolecule.
I see something in the center. Inside. I see something.
Yeah.
I see something inside.
Inside?
Yeah.
Here?
Yeah.
You see, this is the picture with, I would say, lower resolution. So one can see several spots here. Maybe that is a background which can be shown through the open space here.
Okay, other question, please.
Can I ask you, did you try to measure oxidation state for boron inside the polyborane or carborane? Did you try to measure oxidation state for boron atom inside the plastic? What about the level of oxidation state for boron?
In boron clusters?
Yeah. Polyborane, dodecaborane.
Yeah. Okay, I'm sorry, I cannot move it. Are you talking about this kind of structures? Okay. We didn't measure the oxidation state of borons. What was interesting to us was the dispersion of the negative charge. And what is known, and it is not our discovery, it is boron cluster chemistry. As I mentioned, in such kind of molecules, there is a partial negative charge on the hydrogen atoms, and partial and some negative charge on the boron clusters. It may be strange for you that you can see that as well boron clusters as well boron atoms as carbon atoms are 6 coordinated, and this may adapt to what is the let's say oxidation or valency of the boron atoms. But these links which you can see here, they are not real chemical links. They are actually a coordination between the connected atoms. What is even more interesting that this type of molecules, and it is a property of boron clusters in general, that due to the distribution of the charge within the whole molecule, these molecules are aromatic in 3 dimensions. They are aromatic in 3 dimensions. So it is another, I would say, interesting property of boron clusters. As about the oxidation state, we are more interested about the oxidation state of the metal in boron, in metallocarbonates, in complexes with metals, because this affects some interesting to us properties of these molecules.
Okay, so we finish our time. Thanks again for the interesting talk. And we have to invite Dr. Anna Morozovska for the last talk for today morning session, because the scheduled class talk will cancel. So please.
Dear Professor Yatsenko, dear ladies and gentlemen, thank you very much for the invitation to present to you the details of our research. This talk is done by a joint team from the Institute of Physics of the National Academy of Science of Ukraine and from the Oak Ridge National State Laboratory. We mainly theoreticians and our colleagues from Oak Ridge are responsible for the experiments about which I will try to explain you some details. Well, I would like to talk to you about the possibilities of the control of polarization hysteresis by the appropriate choice of the surface screening in thin ferroelectric films. This talk is divided into introduction, motivative part, and original part, and conclusions, what to our mind can be done to lift up this field of nanotechnology of ferroics more close to the applications, to the prognostic level. Well, first of all, let me remind some details. What are ferroics and what is the problems of nanoferroics physics? Ferroics are condensed matter in which, under certain conditions, it must over temperature or pressure, external, or their changes at some temperature or at critical pressure, the spontaneous symmetry breaking appears, and below this temperature, the cooperative phase transition into the ordered states appears. As a result of this transition, the so-called long-range order parameter appears. This quantity, it is a physical quantity. In our case of ferroelectric, it will be a dipole moment of the unit cell. In other more common example, it's magnetic moment, for example, in ferromagnets. Well, this order parameter can be switched between several metastable states to form the so-called hysteresis phenomena. Well, and what is also interesting is that most of ferroics splits into domains. The region with a certain direction of this order parameter below this phase transition, the term below means typically below the temperature or above the critical pressure. But all this is good and well known for many years. The first ferroelectric crystals is about 100 years ago, barium titanate. But the problem is, when you go down to the nanoscale, you decrease the size either of layer, the thickness of the layer, or the size of nanoparticles. Typically, there is some critical size below which no properties like long-range ordering should exist. This may happen to very many reasons. First of the reasons is that there are too small amount of items remaining, and the system has not enough force to establish a cooperation between this. This transition can be called the thickness-induced or size-induced critical phase transition, and its reason is that the correlations becomes too weak in comparison with, for example, simple thermal energy. But typically it occurs below 10 nanometer limit. And the goal of modern nanotechnology of ferroics is to somehow prevent this process. It is to find the conditions under which the ferroic states can remain or even enhance when we go down below 10, 5, or even sometimes 100 nanometers. And the problem here is not only that the property can disappear, but also that the property can change. For instance, most of all know that there are hysteresis and antihysteresis. The difference between them are shown in the bottom of this slide. The hysteresis is a single loop, and the quantity order parameter is a ferroelectric polarization, elementary dipole moment of the ferroelectrics that have a critical electric field, so-called coercive field, under which it changes its direction. The antihysteresis is typical to antiferroelectrics, similarity with antiferromagnets, and here we have a double loop. Well, at nanoscale, I will talk about this. There's two absolutely different scenarios at macro scales sometimes can be mixed up, and also we should know either how to use it or how to prevent. Also, the domain information, which is important for fundamental science and for applications, are typically absent in true antiferroelectric materials, but they are present at nanoscale. Again, I will show you the details. Well, another thing different from the size-induced phase transition is the surface influence on the business. When you have electrically open surface, in the sense that you have some layer, for instance, the electric oxide layer in the system which contain ferroelectrics in film, then graphene channel, and then top gate. This dielectric layer also prevents conservation of the ferroelectric field, of the ferroelectric state. Why this happens? This happens because the bone charge that creates ferroelectric polarization try to scatter in the gap, and the electric field which is formed in the gap decreases this polarization. And in this case, when the surface of the ferroelectric is electrically open or partially open or covered with imperfect screening, it can be imperfect electrode, it can be ambient gas or solution. Well, in this case, the critical thickness is typically much higher than the limit of 10 nanometers. It can be, for instance, several hundred of nanometers or even microns. And this is a problem for the device's miniaturization. So, we should work on the question how to choose appropriate screening conditions which allows us to decrease the critical size and to conserve the ferroelectric state as long as possible, as well as to control the peculiarities of the domain formation. One possible escape is to choose so-called ionic arrangement, because ions also can effectively screen the bone charge. Well, but it is experimental results which are abundant today, but no comprehensive theoretical and especially analytical theory have been evolved yet. Partly because the cases are material sensitive, environment sensitive, substrate sensitive, electrode sensitive, and so on and so on. But nevertheless, we should something do about this, because even if we consider the linear model of the screening, these models are already known in the literature, you may see from this slide that when you increase the screening length of the surrounding, the conditions for the polarization conservation vanishes, and as a result you have additional domain structure, so-called closure domains, at the top surface of the field which is electrically open. Much more interesting situation is for the ferroelectric which is covered by a graphene layer. Graphene is a Fermi-Dirac 2D semiconductor, and in this case the screening in graphene is principally nonlinear, is described by a well-known Dirac equation. And this nonlinear screening leads to the mutual influence of the domain structure of the substrate on the conductivity of the channel. As a result of these nonlinear interactions, the p-n junctions are formed in graphene. Each p-n junction corresponds to the domain wall of the ferroelectric. And in principle, if we can control the amount of the domain walls, their velocity and their formation, we can control the conductivity of the graphene channel, and this can be used in the field effect transistors, for instance. The third case, which is important to my talk, is the case of ionic absorption, so-called Stephenson and Hyland model. They made an experiment, and only then they think about the theory. The experiment was very simple. They take a monodomain film with remote tip electrode and make the distance between the film and the tip electrode exposed to the external oxygen pressure. They can change this pressure. And as a result, they thought that the ferroelectric polarization critically depends on the pressure. At high pressure, the polarization conserves, and at low pressure, the polarization disappears. This result was described by these authors by the so-called Langmuir absorption model. Later on, I will talk about this. And in comparison with the previous model, the Langmuir absorption model is principally nonlinear. So again, it's the mutual interaction of the ferroelectric polarization with ionic state on the film surface. Well, here is our results, better to say results of our experimental collaborators from ORNL. And in those results, you can see that you have a very, very thin barium titanate film. Barium titanate is a proper ferroelectric, and its typical critical sizes are rather high. It can be microns in accordance to the earliest results. To latest results in hand, it can be 100 of nanometers. But in our experiment, when the surface of the barium titanate was exposed to the oxygen pressure, you can see that even a film of thickness 4 monolayers remain its ferroelectric properties. We have a hysteresis loop measured by piezo response force microscopy for this film. Well, how in principle we can quantify all these results and understand which screening is required for a concrete case? We should consider a system which contains bottom electrode, ferroelectric film, which or without domain structure. It should be considered self-consistently. Does this structure form or not under a certain condition? A layer of the screening charge that is covered the top surface of the field, and the electrode. The electrode can be plain or tip electrode, it can be remote or it can be very close. So we should have a possibility to vary the thickness of the gap between the film and the top electrode. And for this model, it is reasonable to consider three main, and to compare, of course, three main models of the surface screening charges. The first is the linear screening. No screening at all, the model with perfect electrodes, which should be an ideal model leading to the smallest critical size. And the model with the gap and without surface charge at all, and this model should lead to the domain formation. To be brief, the mathematical description of the electric part of the problem is rather simple. It is usual representation for the components of ferroelectric polarization. The in-plane components are described by the linear relation with external electric field, and the component perpendicular to the film surface is ferroelectric component, and these components obey nonlinear Landau-Ginzburg-Devonshire equation with the cubic or fifth order nonlinearity. It depends on the transition order in the ferroelectric. The boundary condition is of the third order, and these conditions are typical for the ferroelectric thin films physics. The electrostatic equations are primitive. It is Laplace equation outside the ferroelectric and Poisson equations with an homogeneous polarization divergence inside it. The only thing I would like you to pay your attention, it is that in the boundary condition on the film surface, we have the density of the 2D screening charge on this surface. Well, and further, I will consider three models. As I talked, the model of linear screening, when the density of the surface charge depends on applied electric potential. In this case, it will be overpotential because it will be different from the applied potential, in fact. In a linear way, this corresponds to the Bardian surface stage, for instance, or for imperfect electrodes. Next model is the Fermi-Dirac screening corresponding to the two D semiconductors like graphene or boron oxide. No, better to say about graphene because graphene is massless and for boron oxide is difficult to say. And the third case is Stephenson-Hyland model of Langmuir absorption. And my goal is to compare results for their three model cases. Well, very briefly, first case linear charge density, second and third models nonlinear charge density, but in the case of the Stephenson-Hyland model, we have exponential nonlinearity, and what will be important for understanding of the obtained results is that the ion formation energy can be different for positive and negative charge species. It can be equal, but it can be different. All depends on the types of ions which are located at the surface. And a simple relaxation equation for the surface charge. It's phenomenological equation, of course, we did not derive it, we postulate it. Well, using parameters for barium titanate that was chosen in accordance with available experiments, and sizes which was at the experiments, in real scale, you can see that those densities are very different. The linear density is the highest, but it's linear. And the Stephenson-Hyland density saturates much more often than other ones, at room temperature, of course. Well, and the results are so that for the first model, which is a model of linear screening, the free energy relief is usual double well potential, typical for Landau's theory. When you apply external voltage, one well of the potential becomes deeper, and another well of this potential disappears. Classical phase transitions either for ferroelectric or for a ferromagnetic in applied external field. For the second model, Fermi-Dirac model of the 2D electron gas, you can see that, first of all, there's extremals converging and diverging, blue and red, are not close to one another, and the potential, unexpectedly, the potential cross-section becomes not two wells, but one well with two local extremes. And when you applied external voltage to the film between the top electrode and the bottom electrode, one of the wells becomes deeper, it's okay, but the central well does not disappear at once. And there is some situation when you still have two well potential at big enough applied voltage. And maybe you have here some inflection point. This indicates that you can see the region of the double loops. And after one or two slides, I will show you this scenario. The situation with the Langmuir absorption model corresponding to ion absorption of the surface is even more interesting. Here, the two extremals are far enough from one another near the minimal point, and the potential becomes more flat, but this central minimum almost does not change with voltage increase. It's just falling down. No changes of the well at all. It is related with the saturation density of the Langmuir absorption. This is for equal formation energies of ions. For different formation energy, you can see that the extremals for one type of polarization becomes far from one another, and for other polarization directions, they become more close to one another. As a result, the potential have a linear part in the cross-section and saturating well with a break between this. So in this case, one can expect unusual shape of the hysteresis loops in the system. And let me show the loops. For Bardeen screening model, linear model, this is usual dynamics typical for the phase transition. We have a stone nanometer film close to the critical thickness. Well, at room temperature, we see the loop because the screening charges screen some amount for polarization. It will be 1 micron without the S charge and stone nanometers for the S charge here. Well, when we increase the temperature, the loop continuously vanish, no double loops, no loop distortion, no horizontal shifts, and so on. At 500 of kelvins, there are no loop at all. And the behavior of the screening charge is also conventional. We see a rhomboid shape of the screening charge for low temperature, and no hysteretic shape for higher temperature when the hysteresis of polarization disappears. The situation with Fermi-Dirac model is more unusual, which can be expected from their potential relief. First of all, for a 15 nanometer films, we see no loop at all. We see very thin double hysteresis loops vanishing. And I know that here is a loop, but you probably see only here the thicker at 30 kelvins. And nonlinear shape with temperature increase and almost linear curve green with at 500 of kelvins. The same for the screening charge. The screening charge, we see a nonlinear curve, but without a pronounced hysteresis window. When the field becomes a bit thicker, for example 75 nanometers, we see a single hysteresis loop at room temperature and a double hysteresis loop at higher temperature, and only then the loop disappears. And the origin of these double loops are not related with the order of the phase transition in ferroelectric, as typically is expected for the ferroelectrics of the phase transition order, they can have double loops. No, since the hysteresis take place in the interval of at least 100 of kelvins, it is related with the nonlinear interaction between the ferroelectric dipoles and screening 2D carriers at the surface. The same can be seen from the screening charge, nonlinears maxima, and their eventual disappearance with temperature increase. Well, the situation with Stephenson-Hyland model is more pronounced. Here we can see a clear double hysteresis loop for a very thin film, 8 nanometers below 10 nanometers. Our goal was to show how thin films can be ferroelectric with appropriate screening. And this double loop disappears with temperature increase. For more thick film, 10 nanometers, the limit of true nanomaterials, so-called limit, we have single hysteresis loop at low temperature with high enough coercive bias, enough for applications, and this loop becomes double one with temperature decrease and finally disappears at elevated temperature of high 100 of Kelvin. This situation is for equal formation energies. For different formation energies, we have so-called strongly distorted loop. This loop is either not single nor double. It is so-called minor loop. For one direction of external bias, you have loop, and for another, you have a linear curve. And with the thickness decrease, this loop looks somehow similar to the single loop, but is very truncated and irregular. This is because our information energy is different, and for one direction of the applied voltage, ions help to conserve the polarization, but for other direction, they only help to destroy this. Well, when you make these films a bit thicker, the effect becomes even more large. And for example, for a 15 nanometer film, you have a pretty high coercive window at room temperature and minor loop at 14 or even at 450 kelvins. For 20 nanometers film, you have almost usual, except for this feature, hysteresis loop at room temperature, irregular loop at higher temperature, minor loop at 400 Kelvin and 50, and almost disappearing at 15K. So this allows us to control, if the experimentalists know how to control the ion formation energies, it allows us to control the loop shape just by changing the ionic environment. And this is one of the main conclusions of this work. So, if you would like to control the ferroelectric polarization, you should choose two things. First of all, you should vary the thickness of the gap between the film and your imperfect electrode. Secondly, you should choose the screening charge which is asymmetric with respect to voltage. For example, ionic screening, and its dependence on the applied voltage should be nonlinear. In principle, all those requirements can be realized in practice, and we believed that obtained results indeed can open some new possibilities of polarization control in thin films in different temperature by appropriate choice of the ferroelectric ionic screening. Thanks a lot for your attention, and this talk is partly supported from the European Union Research and Innovation Program under Maria Skłodowska-Curie grant.
Thank you very much for a very interesting talk. So we have time for discussion, some questions. Please. Can you use microphone? Maybe.
A bit more louder.
Demonstrate experiment result, what type of film and technology of
Okay.
The problem is that not only speaker should hear question, but all auditory. So please use.
Yes, in experiments we have barium titanate, plumbum zirconate titanate, lithium niobate film, but the results that are already published, I show them on this slide. It is a barium titanate film. It was deposited on the strontium titanate substrate, so the misfit strain between the film and substrate was small enough, and the top surface of the field was electrically free, but exposed to the oxygen pressure. The distance between the scanning probe tip and the top surface of the film varied in accordance to the goal of this experiment. This is barium titanate from 10 nanolayer to 4 nanolayer film. We also have almost the same results for PZT film, but I do not show them because they are unpublished.
Other question, please. Okay, no questions. So thank you again for the interesting talk. So we finished our science program, and I would like to give some words for Olena with some announcement.
Please pay attention that in 2 o'clock we will have another session which will be devoted to innovation strategy of Ukraine, to ecosystem of innovation, support science, support startups, transfer technology, commercialization. We will have guests from different countries of the world, from France, Lithuania, Sweden, Spain, Italy. It's representatives from different technoparks which share information, how they support technology, how they support scientists, how they cooperate with different scientific group of the world. It can be interesting for preparation different international projects. Also, if you want to find partners for creating innovation. And also it's very interesting and very important now because if you know Ministry of Education and Science of Ukraine now in process of developing innovation strategy of Ukraine. That's why I suppose it is very important to create a good strategy not only for agriculture as it was proposed maybe 1 month ago. For my dream, I wanted that Ukraine move to high technology because we have all opportunity for that. So I invite you. It's in program of conference and it will start at 2 o'clock here in conference hall. And after this we will have conference dinner. If you wanted to join to us, please go to registration desk. Thank you.
Okay, so thank you for the work.